in which you take the large n limit and lambda is fixed. Okay, so you perform this large n limit, and interesting things happen on the gauge side, which we cannot talk about today, but the theory goes to its planar limit, and only Feynman diagrams that can be drawn on a plane or a sphere contribute to the path integral. So it's not like it goes to the classical theory. It goes instead to this particular limit, because the factor in front of the action diverges as if you perform like the h bar to 0, you obtain the classical theory. And this is similar because the n is an overall factor of the action, but there is a subtle difference that also the degrees of freedom of the theory goes to infinity. So there are these two competing effects, and the theory doesn't flow to the classical theory, but flows to the planar limit. And in this case, on the gravity side, you have classical string theory. And so you expect it to be easier than the situation before. The string coupling is arbitrarily small, but you still have to use string theory. And then there is the weak form, which is the most powerful. And you have the large n limit, and also the large lambda limit. So if the Toft coupling goes to infinity too, what you end up with in the gravity side is classical supergravity. Okay, so you can avoid also string theory, you can use just supergravity. And this, of course, is the most useful limits for our computations. And you can use weakly interacting supergravity theory to compute quantities in a strongly interacting gauge theory in the large n limit. Okay, so without further ado, I will move to talk about our particular holographic model that we will use. So we will talk about holographic QCD now, not anymore in general of ADS CFT or some super Yang-Mills theory, but our goal is to compute some real world quantity. So QCD has some differences with the conformal theory we saw before. So what are the theory? What the problems? Of course, yeah, QCD is not conformal because it is a confining theory that generates dynamically an intrinsic scale lambda QCD. Okay, so it has an energy scale, and so it cannot be a conformal theory, obviously. And so what we learn from this is that the dual geometry cannot be some ADS 5 times manifolds X that can be different kinds of manifolds. But anyway, this approach doesn't work. It cannot be ADS 5. It must be something else. So to introduce a scale in the energy, to introduce an energy scale to the gauge theory, what you need to do is to introduce a length scale in the gravity side, as we saw yesterday. And to do this, there are various approaches. So one approach is to give up finding some complicated string solution and to build a geometry that has the desired quantity. And so you can think of this as being an effective field theory approach. So as instead of, like you do with QCD usually, instead of computing quantities in QCD, maybe you build up some effective Lagrangian, some chiral Lagrangian, you can work in the Skirme model. And those are bottom-up approach. So you work on the symmetries and you introduce some factors and some couplings that has to be fitted to data. And it has good predictive power because, of course, with few parameters, maybe you can describe a lot of phenomena without going too much into the complicacies of the real UV theory. And so the bottom-up approach in which the most prominent example is the so-called hard-wall model. Casino. Hard-wall model. And in a hard-wall model, you introduce an energy scale by hand. So you take ADS geometry. You take ADS 5 geometry. And then you say that the coordinate set lives between 0 and some coordinate Z0, which is chosen to fit some data, maybe to fix some mass. Usually it's chosen to fit the mass of the rho meson. And so by doing this, you give up the idea that this should be a solution of Einstein's equation, but you obtain a desired phenomenological quality. So then you can insert gauge fields in this to match the symmetries that you want, namely chiral symmetry. And then you can introduce another field to account for chiral symmetry breaking. Now there is not much time, so since this is not the model that we will use, we will move to analyze the other kind of approach, which is somehow more difficult. It involves a more complicated model, but due to its top-down nature, you don't need to add things by hand. You just have to find where they lie within string theory. So our top-down approach is based entirely on string theory. And of course, we'll have less free parameters because they all come from a theory of quantum gravity. So in 1997, Maldacena builds the construction of ADS CFT that we saw yesterday. And of course, there was great interest in pushing it towards confinement. And just a few months later, Witten develops a confining geometry in type 2A string theory, as I anticipated yesterday. And in 2004, Sakai and Sugimoto, they added flavor to this model. And so this is why this is called the Witten-Sakai-Sugimoto model. From now on, if I write again, WSS will do. So let us analyze how this background looks like. So now we talk about Witten's background. So we take a stack of branes again, not much fantasy in that, stack of NC, and those are D4 branes instead of the D3 that we saw in the work of Maldacena. And the corresponding solution, now I will not call again the general formula, but you can verify, is this. And plus some function plus another factor which is the inverse of the one before, and the u squared over f of u plus u squared, and this is a factor that is a fourth sphere. And then you have the other fields of supergravity. Of course, we already told that to give a solution means to give also a dilaton. U over R the 3/4. The corresponding field strength of the Ramond-Ramond form, which is in this case the F4, which is the C3, and so the flux of this fixes this value. Now I tell you what all those quantities are, and then this function u is given by this formula. Okay, some quantities have different names because of the notation I used usually, but it's not that different. So this coordinate u is essentially the same as the r that we saw before, and this ukk is essentially the same as the L we saw before. And so this quantity here is the volume of a four sphere, and this quantity here is the volume form of a four sphere. So this is a four form. Okay, so let's analyze this geometry. So we recognize this part that asymptotically is Minkowski, and so here lives QCD, or like would be QCD, like the one that we want to be QCD. And then we have this direction here. This is our direction, the holographic direction, let's call it, the one that goes into the bulk of our space-time. Holographic direction. And this is a four sphere. If I can write here, for sphere, but it's not interesting for us. Will always be quite trivial. We will not take any fields to be excited along it. But with respect to the stack of D3 branes, we have also this interesting direction here. This is an additional fifth dimension that seems to add up to the dimensions of QCD. Now let us define some quantity. So our R squared is given in terms of quantities of strings by this formula, okay, just for curiosity. But let us now look at the most interesting things of this geometry. Why is this an improvement? So this factor here tells us, when we look at this geometry here, that geometry ends at u equals ukk. And if we want to prevent singularities to happen at this point, so we want to avoid singularities, at u equals ukk, then what happens is that the coordinate tau has to be periodic. With a period, which we call delta tau, of 4 pi over 3 r to the 3 halves ukk to the 1/2. Okay, so this is the period, and if we look at it with also its factor f of u, we see that this is a circle that as you go down into the bulk, shrinks, and its radius goes to 0 when you reach UKK. Okay, so the U-tau subspace has a very interesting shape. So we have the U-tau subspace, which looks like this. So if I can draw properly. Okay, not that bad. Okay, so this is what is usually called a cigar, because of its shape that reminds of a cigar. And you see that it achieves the same feature of the hard wall, in that the geometry at a certain point simply ends. But this ending is dictated by Einstein equations, and it ends smoothly. And locally around this is called the cigar tip. Around here, an observer there feels flat space. This compactification of the fifth dimension, which is welcome, of course, because you don't see a fifth dimension in QCD, even though this circle will never be able to be very small, to be in the phenomenologically relevant parameter regions. So we will always have this ugly circle additional to real QCD. So this is almost QCD. But this compactification introduces a mass scale, which we call MKK from Kaluza-Klein. And this is 1 over the radius of the circle tau. So it's 2 pi over delta tau. And it's 3/2 UKK to the 1/2 over R to the 3/2. Okay, so this is the characteristic energy scale of the theory. And this is the mass scale that gives the mass gap in the spectrum of glueballs, for example. At this stage, the theory is pure glue. You only have gluons. And now we can take a look at how confinement arises in this model. So let us talk confinement. So confinement in from a sketchy point of view, confinement has to do with the potential between the two, let's take a quark anti-quark pair, and the potential between them, if this is some delta x at large distances, we want that it goes like delta x. And so these signals that the theory is confining. Okay, so if we take Polyakov loop, which is a temporal Wilson loop, in the gauge theory, so you can compute this essentially rectangular loop in which one direction is time and the other is a long space. And so this represents two static quarks with a flux tube that connects them. And if you compute this and it gives you an area law, then it signals confinement. Okay, so holographically, how is it realized? Okay, let us take this temporal Wilson loop that lives on the boundary of our space. So I drew it a bit tilted. And to what it is due? To what is dual this object? A Wilson loop is dual to a surface that probes into the bulk of the geometry, and whose boundary is the Wilson loop. Okay, you can see it as a string worldsheet. So a string will want to hang down and then you will have some surface for this object. You compute the surface, and this is dual to the Wilson loop. And it is not immediate to see, but if the geometry is warped, the string will want to probe down deep into the geometry instead of staying in which looks like the minimal area, which is, of course, this rectangle here. So in general, if the geometry has no cutoff and is heavily warped, then the string will probe down, 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 and you will not feel any, it will not produce any area law. But what happens instead if you have this cutoff to geometry is that the string will want to lay down, but then it encounters the cutoff, and so it will produce this structure, of course, a bit smooth on the edges, but essentially that's what happens. And of course, it will produce an area law because this will be the one that contributes the most. And this is something that you see for great separations. And from an equation, from a string theory point of view, what happens is that the effective string action of this string that hangs with the boundary conditions to be on the Wilson loop, you can compute it. So you have the Polyakov action, and from there you can read the string tension. Okay, but the string tension is you put a constant in front, and that's the string tension. But it's for this string. But for the QCD string, the strings that see QCD is instead this string. It's the 4-dimensional string, not the 5-dimensional string. And so you have to integrate along the Z direction and obtain the 4-dimensional action. And so what you obtain is that on top of this vector here, you have this vector here. Because it carries the determinant of the metric. And so it's an effective string action. And what you end up with is U over R to the 3 over 2. And so for large values of separation, it wants to lay down and produce this effect, and it will scale as an area law. So apart from the precise computation, this is what happens in the geometry. Okay, now let us move to the part that is most interesting to us, because we want to describe baryons. And so as a first step, we need flavors. We need to add flavors. For now, this world is pure glue. You only have gluons, and they form glueballs. And the theory is confined. So you have glueballs, you have a mass spectrum for glueballs with the mass gap of order mkk. But we want quarks, antiquarks, mesons, baryons. We want QCD. So to introduce flavors, what we do is to add the stack of NF pairs of D8 anti-D8 branes. Or we didn't talk about anti-D8, but okay, they exist and they carry negative values of Ramond-Ramond field charge. We saw that they are sources for Ramond-Ramond fields, and so the flux of these Ramond-Ramond fields can be positive or negative. You have D8 or anti-D8, and they can annihilate with each other. So you add those couples, NF of each one, and you separate them along the circle. And so what you end up with is that if you have the dimensions, let's call them 0, 1, 2, 3, 4, 5. Instead of 4, let's call it tau, so it's easier. 6, 7, 8, and 9. And the D4 and the D8 branes are positioned like this. So the D4 extend along these first directions and along tau 2, while the D8, they extend along, well, we want them along the Minkowski space that will be QCD, because we want our flavors QCD, and they must have a 9-dimensional work volume, so only one coordinate will be excluded, and it's tau. So the stack of D4 and D8 is transverse in the tau coordinates. And we put this construction in all the string action, the DBI action, and you can look for the shape that they must assume for the embedding. It has scalars, the degrees of freedom that describe the embedding. And what we find is that in the U tau subspace of the cigar, since it's bounded, and since they are transverse in this direction, but they probe all down the holographic coordinate, they will form a curve in space. And so let us put the D8 and the anti-D8 antipodal at infinity, and they are forced to join and meet. At the cigar tip. Okay, so there is no other choice, essentially. And this is a stable configuration. You can write down the equation of motion and solve them. And so they join at the cigar tip, and they end up forming a single stack. And this is very welcome, because you can see this as going from a UNF times UNF symmetry group for the two stacks of branes with their gauge fields. And you go to a UNF. And so this is a geometric description, well, or realization if you want, depends on how you think of this as being fundamental, of spontaneous breaking of chiral symmetry, chi SSB. Okay, so it is a phenomenon that happens here and happens from the geometry and how you introduce the flavors. Okay, it's very good. And so since we want to create an effective theory of flavors now, we want to look at the theory on the word volume of these branes. So we choose new coordinates, and okay, yeah, let's write all the changing coordinates. We choose new coordinates, and so we perform these changing variables. And tau is instead UKK. Here, let's introduce an angle theta. So first we exchange these coordinates for somehow, this you can see as being a polar system. If you look at the cigar from the top, and you can look at it by starting from the cigar tip and giving an angle and the radius. And this was the tau coordinate essentially. And yeah, it's a tau coordinate rescale, this radius, this angle, of course. And then we go to a new set of coordinates in which y's are sine of theta and z is r sine of theta. So all this madness to end up with some usual Cartesian system of coordinates in which you have some Y, and Z. I don't know if I put the correct ones in the right place, but it doesn't matter. What's matter is that the Z coordinate is taken to lie along the stack of the branes. So Z now is a coordinate that runs along the branes, and Y is a coordinate that is transverse to the branes. So it's very convenient for our description. And Z goes from minus infinity to plus infinity, and the 0 is in the middle. Okay? So in the end, the picture that we have, for clarity, let us report here, instead of having that top view. So in red, I put the stack of branes, which are antipodal at infinity. And then in gold, our original coordinate system, in which you have a tau, and you have a u coordinate, which goes all the way to infinity. And then in blue, I sketch where lives the z coordinate. And this is z. And here you have a 0. Okay, so, and transverse to this, you would have the y, but we don't need the y. Okay, so now that we have coordinates, let us move to see how this world volume gauge theory looks like. We already introduced the pieces of the action necessary. We just need to specialize them for this situation. So let us introduce notation. Always be clear. The gauge fields that live on the D8 brane, we call them A with this curly writing, and it's A alpha dx alpha, where alpha goes along all the 9 dimensions of the, well, 9, let's say 5, because we don't take the field to be excited on the 4th sphere. And we can decompose it in the subgroups as an abelian part, normalized with this factor, where NF is the number of flavors, and this is the identity matrix, plus the non-abelian part with the matrices that form a base for this group. And so from now on, we will work in the situation in which we have 2 light flavors, so up and down flavors, essentially. This is because in the end, we want to compute some quantities of the nucleon, and we just need up and down works for it. And in this case, these matrices can be taken to be half of the Pauli matrices. And so this expansion looks like A alpha equals to A alpha half plus A alpha tau A. And for the indices, I will follow the following notation, where alpha can be 0, 1, 2, 3, z, so every indices that we use. Y and all the Latin, like J and so on, will be 1, 2, 3, so space-like in our QCD space. The capital Latin starting from M will be space-like, but including also the holographic one. And the Greek starting from mu, as always, will be the usual Minkowski one without the holographic coordinate. Okay, so it's a bit of an effort, but will prove useful when reading stuff. Now we want to derive the effective action. Okay. Action of the D8s. Okay, DPI action we expand the square root, take the trace and all this stuff at quadratic order. And this is a bit annoying, but you can, if you want to do the computation yourself, you can exploit the fact that the metric is diagonal while f alpha beta, let's call, is antisymmetric. So it's easier than it could be. And what you end up with is this nice action. Trace e for x the z. You have 1/2 a function of z f mu naught squared plus k of z f mu z squared. Okay, so this action will be essentially the protagonist of all our work. And you have a 5-dimensional Yang-Mills in a warped space. And these functions k of z is equal to 1 plus z squared, and h of x or h of z is 1 over 1 plus z squared. And I'll be honest, I don't remember if it's 2/3 or 1/3. It's 1/3 or 2/3. I don't remember. It's details that are not that important now. But I think it's 1/3. And for shortness sake, we will call this overall factor k. So we have an easier time later. But we also saw that this is not the only action for a D-brane. We also have the couplings to the Ramond-Ramond sector. So there is also a piece of action for these D8 branes, which look like, I mean, in the background, we have a C3, which is different from 0. And so this can couple to our branes. And this can couple via an action, which we call the Chern-Simons term, which is 1/48 pi cube integral over the D8 world volume of C3 wedge. And then we have F wedge, F wedge, F. Okay, so 6 plus 3 equals 9. And we have all the dimensions we want. We integrate by parts. And this F3 becomes its field strength F4 that we can read from the background. And this other form becomes a thing called the Chern-Simons 5/4, which we now will write. And all of this in the end becomes NC over 24 pi squared. I'm just taking the F4 from the background. And there remains a integral over omega 5. And this omega 5, if someone of you worked with the Chern-Simons theories, will recognize it. Otherwise, this is given by the trace of this object. Minus 1/10. And then you have A. Okay, now I didn't write all the products are taken with the wedge product. But I don't write, otherwise they all look like A and wedges and took forever. And we can already see that for our U2 group, this will go to 0 because it's an antisymmetric combination of these 5 objects, but the group dimension is 4. So at least we don't have it. And when you compute everything, the final action, called the Chern-Simons action for this theory, is simply this one, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, integral over d for x to z. And then we have the abelian field that multiplies this alpha 2, alpha 3, a, f, alpha 4, alpha 5, a, and the same for the abelian, the alpha 2, alpha 3, f, alpha 4, alpha 5. Okay, so we have 2 pieces of the action, Yang-Mills and Chern-Simons. Okay, now I want to talk about this being a theory of mesons. I don't know if it's too long, but we will try. So we have a theory with an action. We derived an effective action, 5-dimensional, in which one of the dimension is the holographic one that probes into the bulk. And we see that we have our gauge degrees of freedom for this theory, and they should represent flavors. And by the way, we saw that the chiral symmetry, which is a global symmetry in QCD, has become here a gauge symmetry. All right, so that the real chiral symmetry is encoded here on symmetry transformations that reduce to a constant transformation on the boundary, and it becomes chiral symmetry. But on the bulk of the geometry, this is not restrained to be a global symmetry. So let us talk about how this theory then realizes mesons. So in a certain sense, we already did, because after we broke this chiral symmetry, the fundamental degrees of freedom of this theory are now mesons, and these gauge fields, where we had this gauge fields for the de Bruijn and anti-de Bruijn that you can see as being for left and right chiralities. And now you have a single stack of branes and a single gauge field, and this gauge field should describe mesons. But to see it, let's expand these fields on an ansatz. So for a mu, we take the sum of b mu n of x and psi n of z. And for a z, we take a similar form, but this time it's a scalar times some other function phi of z, where these psi and phi each form a complete set, are complete sets. Okay, so we assume that there is, you can expand these functions. In general, they're complicated function of x and z, but you can expand them on factorized, on a sum of factorized terms. So when you plug these objects in the Yang-Mills action, what you end up with, okay, we'll write the 5x from now on to be shorter, a double sum of m and n, and you have 1/2 k of z, and then you have the mu phi m, the mu phi m, and then you have this other phi, which is called also phi, plus, then you have b mu n, b mu m, z psi m, z psi n, minus 2 the mu phi m, b mu n phi m, the z psi n, and plus 1/4, and there is the z part, which is easier, luckily. F mu nu m f mu nu psi m psi n. Okay, so we obtain this monster here. But okay, we want to impose some normalization and orthogonality rules for this function psi and phi for the z-dependent functions, and we take a look at these pieces of the action here, this one and this one. Why these ones? Well, because by integrating them, we can impose these conditions. So we choose the functions to obey these rules. So we take the psi m to be solutions, to be eigenfunctions of these equations, of this operator, essentially. Okay, with eigenvalues lambda m. And then we impose a normalization and an orthogonality rule. So they are orthonormal with respect to this kind of product, you can say. Okay, we are free to choose these things, and we can take a look at these two terms here and see what happens. So the Yang-Mills part. So this is essentially the part of action that regards a vector, because it involves b mu and its field strength, while these other ones involve scalars. So we are looking at the action for vectors. And when you integrate over z using the relation we introduced before, you end up with this n, sum over n, 1/4 f mu nu n f n mu nu plus 1 n mu. So haha, what we obtained here is a kinetic term and the mass term for the vector field b mu. And so we see that this theory has as degrees of freedom an infinite tower, has in its spectrum an infinite tower of vector meson and predicts the masses with mass squared lambda n. Okay, so once you fix the energy scale, that eigenequation gives you these eigenvalues that are dual to the masses of mesons, essentially. And this is very cool. So this is not only an effective field theory like the Carlo Lagrangian, in which maybe you make a theory with baryons, but here you have infinite tower of vector mesons. And you don't have to put it by hands or to insert its effects in some couplings between pions. Now we have to analyze also the part with phi, and to do so we choose some rules also for the other set of functions in Z. So we choose this rule, phi m phi n, well, again to a delta. And if we employ this, we can choose phi n to be equal to a derivative of psi with an overall factor given by the mass. Or we can even say better, something like square root of lambda n. And this is true for each n, let's say, that starts from 1. Okay, for each of those functions psi n, you can have this phi n. But if you want a complete set, you have to pay attention because there is another function that is orthogonal to each one of these. And this function, we will call it phi 0. And is to have the same normalization. It is like this. Okay, so this one is different from the others because it has not a corresponding mode in the vector meson tower excitations. Okay, so now we can perform a gauge transformation of the field B. And I think this is the correct sign of the thing, yes. And if you do this, the ugly term here gets eaten. And what you end up with is that your Young-Mills action in 4 dimensions, as obtained from this holographic model, is this one. Okay, and so we have the same as before, the vector mesons, but we have a single scalar field here, which is massless. And what is a massless scalar field in a theory with massless quarks and chiral symmetry spontaneously broken? This is a pion. And at this stage, this is 1 because we worked with only the abelian fields, essentially. I didn't take any traces, and I treated all of these as commuting fields. And to have a simpler computation, we did with the gauge symmetry, with gauge group 1. So I should call it eta prime, not pion, but there will be the analog for the SU2 part of the group, and this will be the pions. All right, so we have massless pions, and this means that we have massless quarks. Okay, because if we introduce a quark mass in the theory, then the chiral symmetry is explicitly broken, and then the Goldstone bosons of chiral symmetry breaking has mass. And this is exactly what we want to do now, because many computations can also be done without quark masses, because they are small anyway compared to the mass scale of the theory. But if we want to compute, for example, the neutron electron dipole moment, which I will want to do soon, you need to have non-zero quark masses, because otherwise it becomes 0 automatically, because the effects of the theta angle in QCD is non-physical. So to add quark mass, you immediately start with a problem. So in a quantum field theory, in a regular quantum field theory, in your 4-dimensional space-time, what you do? You usually write some local term, which is like psi L, psi R, something like that. But for us, let's put some these brackets, how you call it, L and R fields, fermions, are separated. In the tau direction. And so no hope for local terms. So the best you can do in this theory is to construct a Wilson line that goes from one to another along the circle. So what you can do is to insert in your dual of your almost QCD an object which is an open Wilson line, which is built essentially like this, and it's evaluated at x, and tau equals minus pi over 2 radius. And then you have the path integral of the exponential of the integral in dx4, dx4, and actually it's dx4, not the 4x, because it's the circle, and because sometimes it's called dx4, let's call it the tau. I a tau plus some scalar field in your Yang-Mills theory, and then psi j x, and it's evaluated on the other side. Okay, so this is the operator on the field theory side, on the gauge theory side. So essentially what we are now doing is to take our Seeger with the D brains, and we are saying that our QCD lives on the boundary, and so we insert, instead, we cannot construct a local term, so we insert this open Wilson line here. And we already learned Wilson lines, what kind of duals have. They have some word sheet of strings that have this line as a boundary. And so the dual operator will be some string action, because word sheet has this as a boundary, and your D-brains, okay? These and the other side, of course, but because of symmetry reasons, that there is no side that they contribute the same. Okay, so this work is a bit complicated, but has been done by Aroni and Kutasov, and that's why I usually call this action the Aroni-Kutasov action. And in the end, when you compute the on-shell Nambu-Goto action of this string that hangs in this portion, you obtain a constant C, which is part of the integration involving this Nambu-Goto part. And we will see that this is related to the chiral condensate. And then we have the integral over d4x of the trace mass matrix of quarks. So it's an NF times NF. And you have e to the minus s interactions minus 1 plus complex conjugate. And so this thing here is in the interaction between the endpoints of the string with the D-brains. And it carries a factor, which is minus 1 minus psi a z, the z, because of course the endpoints interact along this direction only. Okay, then it's a bit complicated, but we just have to take into account the presence of this action too. And from now on, our mass matrix for the quarks will be diagonal and degenerate. So we have M times the identity. Okay, we take two equally light quarks. Okay, and now we are almost done to compute our electric dipole moment. We miss two ingredients that I will tell you about after a small pause. And the ingredients I anticipate are the theta angle of QCD. And of course, if you want to compute the electric dipole moment of the neutron, and we have a theory with only mesons and glueballs, it doesn't really work. We need baryons. Okay, so I think that we can stop maybe 5 minutes, and then we finish.
Okay. Let's stop for 5 minutes, so we resume at 12 past 11. So, are there any questions for now? So, if not, I have actually a question. Curiosity, maybe it's a stupid question, but so you said at the very beginning that you work in the large n limit, so in the large number of colored limit.
Mm-hmm.
And of course, you want fermions because you want baryons in the end. However, in QCD, we know that in the large n limit, the contribution of fermions is subleading if we stop at the leading order in the 1/n expansion. Although this is not completely true, because we know that there is actually some fermionic contribution. For example, the eta prime contribution is not subleading in 1/n. But if we forget for a moment about this exception, we know that fermions are subleading in 1/n. So in this theory, what happens? Because you work in the large n limit, so what happens to the fermions?
Well, actually, if you work with the so now you work in the large n limit, and what happens in that limit is that essentially you can neglect the back from a string theory point of view. Then I have to think a moment about the gauge theory, but you can, if you add a finite number of flavors and then you take the large n limit, you can neglect the contribution to the geometry of the D8 branes. So this is exactly what I did now. I did not introduce gravity, the curvature in space of the D8 branes. So I just placed them there, and they do not modify the background. Okay, and so this would correspond to the quenched quarks approximation, but I'm not very familiar with that. Anyway, as always, depends on what you are trying to investigate. Like if I am trying to address physics of fermion, of course, in that part of physics, they will not be subleading contribution. If I want to observe quantities of a neutron, and the very fact that there is a neutron, you need some fermions, even if they are subleading effects in the whole theory, they are leading to the physics of neutrons.
So you have to get the right power of 1/n.
Yeah,
in some sense.
Yeah, essentially, yes. You can. I mean, what you do usually is that you never really take just the leading order in 1/n. You even after deciding to study fermions, you can just employ a power expansion in 1/n and take also next to leading order. And this is a bit tricky because 1/n and 1/λ corrections would also require to be very careful, because you cannot just take this supergravity configuration, for example. You should account also for all kind of string theory corrections, and also for the resonances along the circle S1 we are essentially, for now, we are a bit forgetting that exists this circle, and that the theory is not really QCD because of the circle. But in reality, it ruins a bit of stuff. And it becomes also manifest when you increase, when you put the theory with finite temperature, the theory reminds of all these higher dimensions and doesn't fit particularly well. I mean, qualitatively, yes, quantitatively, less. So yes, you can perform a 1/n expansion essentially.
Okay.
And for example, for baryons, the static, if you take static properties, right, they're the leading order, but when you make the baryon move, both in space, both you give momentum of its center of mass or you make it spin, those are both 1/n corrections. So you have to account for them in a 1/n expansion. Okay.
Thank you. So if there are no questions, I think it is already the time to resume the lecture.
Okay. Okay. So yeah, I was talking about the theta. Okay, yes, we miss the theta angle and the baryons. So let us talk about the theta angle. What is the theta angle in QCT? Okay, it's a Lagrangian term that you can introduce. I mean, it's permitted by the symmetries. So in principle, it's present. And it reads like this. Trace. No, G mu1, I put them this way. So it's G mu1, G mu2, G mu3, G mu4. And so G is the field strength of the gluons. I didn't call it F because not to create confusion. And this whole object is of topological nature. It's always proportional to an integer times theta. So n is integer. Okay, so being topological, we already saw for other quantities, but being topological means that it has no effects on the equations of motion or on classical physics, which is governed by the equations of motion. But it, again, as it was for the string theory, Einstein-Hilbert action, it enters the path integral. The path integral as e to the I n theta. And so it enters quantum physics and also is an angle because it's a phase. And the other property is that it breaks CP. And this you can understand without many computations, because if this was abelian, it would be a term that looks like E dot B. And this term breaks CP. So it's the non-abelian version of a term like this. And CP is not protected anyway, so you can break it. There is no problem. But the thing is that if it breaks CP, it induces some observables to be non-zero, non-vanishing. And so the most studied is the electric dipole moment of the neutron. So you take a neutron, you place it to an electric field, and watch how its energy states change. So other properties of this theta angle are a bit peculiar. One is that under an axial transformation, it shifts. Theta goes into theta plus 2 NF alpha, where alpha is the parameter with which you rotated the flavors. And so theta can be set to 0. And so it looks like it's not physical. And it is not physical if you don't have massive quarks. But if you have massive quarks, the physical theta, let's call it theta bar, is given by theta plus the argument of the determinant of the mass matrix. Okay, so these are the properties. So if you want to have an electric dipole moment for the neutron, you need to have massive quarks. Otherwise, theta is not physical. And if theta is not physical, CP is not broken. And if CP is not broken, you cannot have CP breaking observables. Okay, so let's hunt for its holographic dual. This term involves the physics of gluons, and so we have to look for its dual in the action for the D4 branes that generated the background. And it is easy to see that if you have the coupling between the D4 and the C1, it looks like this. Where you have the string length factor mu1, mu2, mu3, mu4 integral over the circle S1 of the one form of Ramond-Ramond integral over the other four directions of the trace of G mu1, G mu2, G mu3, G mu4. Okay, so I call them G again because these are the field strength of the gauge field on the D4 branes. And so it is now manifest that this object here reproduces theta. I mean, of course, you have to take the appropriate direction for the legs of these forms. But if you do, what you end up with is theta equal to 1 over string length integral of S1 taken on the UV, where UV means essentially the U1 at Z. Let's call it U equal infinity, because I could use Z, but these D4 branes in principle don't know of the presence of the D8 by themselves. So, and then you have 1 over LS integral on the cigar of F2. It's the same. Okay, this is the boundary of the space, and this one is DC1. So it's using Stokes. You can relate them. Okay, now let's see if this proposal is correct by analyzing its properties. You want to reproduce the properties of the theta. So the D8 brane couple to the C7. So now essentially giving theta to QCD for us is dual to give a vacuum expectation value to C1 in string theory. Okay. So at this stage, we also can have a coupling between the D8s and C1. And how it happens? It happens via the coupling to the C7. It's more manifest this way. The action reads like this: C7, wedge, F, wedge. This is a Dirac delta along the Y direction to have it 10-dimensional essentially, but it's not needed. And this reduces to trace, and you can integrate by part. So this is 7, wedge A, wedge again the delta, and so this is D8. So I can write very fast. Sorry, F8, wedge A, wedge delta. But now we can use a thing that I didn't mention, but which is implied within the Ramond-Ramond sector. That is that the field strengths are duals. In which sense? Well, you have 10-dimensional space, so a P form is dual to the 10 minus P1. So F8 is dual by Hodge duality to the F2. And so we have trace of the Hodge dual of F2, wedge. And So you see that here appears our C1 essentially. And the trace here selects only the abelian component, because we have the trace over only a gauge field here, and only the abelian part survives. And this is interesting because chiral symmetry is encoded in the abelian part. So the equation of motion for the C1 form now are given by d star d C1, and this comes from the kinetic term of the C1, which I didn't write here, but is part of the supergravity action. And here you have this source essentially, NF d star A to NF wedge delta epsilon the epsilon. But we immediately see something now, that this implies that a gauge transformation with a parameter lambda on A implies a gauge transformation on C1. And this is a non-trivial effect because C1 has in principle nothing to do with these D8 branes, but there is an inflow of this gauge transformation from one to another. And so let us quantify this gauge transformation with parameter lambda on the A field. So this is a U1 transformation. And this comes from the normalization of the group, but it's the same anyway. Those are normalization factors. Induces a gauge transformation on the C1 field given by string length NF lambda, and then you have a delta y, the y, and this on the field strength like LS NF the lambda wedge the same delta. Okay, now this is interesting. We perform a gauge transformation and also C1 changes. This looks very much like the axial shift of theta, and we can quantify because delta theta will be the integral over ds1 at infinity of the variation of C1, and this is NF lambda evaluated at plus infinity and minus infinity as a function of zeta. Because this is a gauge transformation, it's not global. It now becomes the axial symmetry when we go to the boundary. And so the axial part of this gauge transformation is one for which it assumes opposite values at infinity and minus infinity, this function lambda, and we can call it alpha. So we use the same notation as before, and it's 2 NF alpha. And so this is exactly the axial transformation. And now we want to note that in the action of Aronov-Kutazov, we have quantity. We have m to the e to the minus I integral of az z. And this includes the abelian field. And so if we choose to eliminate theta, so we choose to eliminate the C1 essentially, we have to choose alpha equal to minus theta over 2 NF. And what happens? That now this action reads mi theta over NF. And so we have phase in quark mass matrix. And so again, if we didn't have a mass matrix for quarks, then we could eliminate theta from the theory. But since we have a quark mass matrix, theta is a physical parameter, and the physical quantity is a combination of both. I can choose not to eliminate C1, but to eliminate a bit of it, and what goes away goes into the quark mass matrix. Okay, for us now, all the theta will be in the quark mass matrix because it's easier to handle than the Ramond C4. Okay, so it has all the qualities of theta, which is kind of remarkable. And we add our last ingredient, which are baryons. And I wanted to talk a lot more of baryons because actually that's the main research topic I follow, but we don't have a lot of time and it would require a lot of effort, which is absolutely not needed for our results anyway. So let's see how they emerge. So we take the leading term in lambda, which is the Yang-Mills action. So we have a Yang-Mills action, and we assume that it admits, Yang-Mills action in flat space admits solitonic configurations. Okay, if you go to the Euclidean space, to Euclidean time, sorry, you have instantons because you have 4 flat dimensions. And we don't need to do it here because we already have 4 dimensions. We have the holographic one, which is an additional space dimension. Okay, but they are not flat. But I told you that along the cigar tip, locally the space is flat. And actually, the things wants to live there because the curvature pushes them there. And so if we assume that solitons of this theory have small size, then they will feel very little curvature around the cigar tip. And so maybe using the flat BPST instanton, which is solution of Yang-Mills equations, is a good approximation, or at least a good starting point. So we take BPST instantons, which are built in this way. So AM is equal to minus I f of psi g dm g to the minus 1, and A0 is equal to 0. And psi squared is the distance in the 4 dimensions of space as measured from the center of the soliton. This big X and big Z are coordinates that indicate the center of the soliton. And this is a square, of course. And G is this function. And F is this function. Where rho is called the size of the soliton. Okay, so this is a complete description of our BPST instanton at the classical level in a static configuration. Doesn't depend on time for the moment. So we use this as a trial. We plug into action, and we look at the next to leading order, what happens, because we didn't solve all the equations of motion, we just solved the leading part. At next to leading order, the Chern-Simons term sources a field A0 abelian, because we have a coupling, if you remember, which is like epsilon 2, 3. No, that's not called mu. We have a coupling that looks like this: M1, M2, M3, M4, and then we have A0, and then we have a trace of FM1, FM2, FM4, and Z, and M5, so M4, M3. Okay, I skipped the 3. Here's the mystery. M3, M4. Okay, we have this kind of coupling, and this object here is the instanton number density, essentially. So the instanton, the presence of the instanton sources in electric field. And you can write the equations of motion in this situation, which is minus k dn f 0n plus nc over 1 and 28 pi squared epsilon m1 m2 m3 m4, and then you have f m1 m2 f m3 m4 plus f m1 m2 f m3. These vanish because am abelian is 0. I mean, they appear next to leading orders. So for this order here, they're 0. And here we have what we wanted. And you can solve this equation, which involves a Laplacian of a 0. And in the end, what you obtain is this a0 and c over 8 pi squared k 1 over xi 1 minus rho to the 4th xi squared plus rho squared to the 4th plus a constant mu, which is dual to chemical potential, but for the moment we don't care about it. Set to 0. We are not solving a problem where we need chemical potential. Okay, now there are two competing effects. You have curvature versus electric field. So you have this soliton, which is a spherical object in this limit, and you have curvature that wants to shrink it along the z direction, but you have an electric field that wants to expand it. Okay, and they find the balance. They find the balance and stabilize the size of the soliton to a certain value. And what you find is that this is of order 1 over k, and k was proportional to lambda, and so the size is proportional to lambda to the minus 1/2. And so in the large lambda limit, this description of baryons is indeed reliable because the size is small and they don't feel a lot of the curvature, which was the premise. Okay, then what happens is that you want them to be also time dependent, and you can introduce, we already have some moduli for these solitons, which are parameters that send a solution of equations of motion in another equation, in a solution of equation of motion. For example, this x and z are moduli, and the rho is a modulus, but of a symmetry that is broken, and so it is fixed by the potential. And there are other moduli, which are called A, and you can make them time dependent. And A is the modulus that is the modulus of SU2 orientation. Okay, so you can think of it as being decomposed like A4 plus I, A, I, tau. So it is a matrix like this. And it's time dependent because the soliton can rotate in isospin space. And we don't need these details just for completeness. Will happen some modulus, but we'll have a minor effect later. And one last thing is that we move to the singular gauge, which is easier for our computation. And the soliton have this form after we do this. A g to the minus 1 dm g a to the minus 1. Okay, so it's similar to before, but this SU2 orientation appears in the solution. So it has not the standard, so it's the standard orientation, but it's rotated. And this rotation can be time dependent. And what we also will need after, we will also need since we are interested in effects that depend on the mass term, in the Aron-Kutazov term, there are integrals of this AZ gauge field. And so we will need the exponential of I integral of AZ dz. Okay. And we can expand this as minus cosine of alpha plus I sine of alpha. R is a unit vector times tau, where alpha is a function of R because we integrated over Z, so it's only a function of three-dimensional distance, and it's pi over 1 minus rho squared over R squared. Okay, so this is everything we need to do our computation. And so now we move fast to compute our electric dipole moment with all the information we have. We have baryons, we have theta terms, we have mass terms, we have this integral calculated, and so it's a lot of stuff, but we already did everything. So there will be absolutely no problem. And so let us start. So theta enters the Aron-Kutazov action, and then it will provide equations of motion for AZ and AZ hat. Okay, because there are the Z components in the Aron-Kutazov action. When you differentiate, only sources for these equations of motion appears. So what is our strategy? Our strategy is that without the theta term, you have the baryon, and without mass and theta term, you have the baryon that we described before. So we use the perturbation approach, the perturbative approach. So the baryon is perturbed. So we expand the baryon as a background solution, which is the baryon we already described, plus some small perturbation, which will appear at order m theta. And now we know that the mass of quarks masses of quarks are small with respect to the mass scale of the theory, so it's safe. We know that theta should be very small, compatible with 0 also, so it should be safe. But moreover, those are perturbations also subleading in lambda. And so there is another aspect that in the large lambda expansion, there is also this aspect you can perturb by considering 1 over lambda corrections. And we will write now the equations of motion, which are big set and quite ugly. I will tell you what is this phi, but it's 0, so this is why I didn't tell you. So sine of alpha, sine phi, xk over r, a, to the -1. Then we have another equation, which is h of z. To 0, and then we have 2 more. 4. No, okay, now we have 2 more. And now we have the ones for the 0 components, which are minus k. Then we have h of z, then f 0 nu plus z k of z delta f 0 z minus nc over 32 pi squared epsilon ej kappa, and then the variations of these fields fij a fkz a plus delta of fij fkz abelians equals 0, and the last one, which is the non-abelian, and the z k z f 0 z minus nc over 32 pi squared epsilon jk, and again the variations of fij times fkz, and this one is abelian and the other not, and this is faz fjk, and the second one is abelian, and this is equal to 0. Okay, so now we have this monster set of equations, and we want to solve them. And we immediately want to look at what can be simplified. And we know that on the background, AZ abelian is equal to 0. But in fact, also every AI on the background abelian is equal to 0. But this thing in particular implies that phi, which is the same as before, is minus psi the integral over the z of AZ abelian, then this will be 0. And so let's zoom on our sine of phi is 0 and cos of phi is 1. Okay, so this equation, so you can label this equation as for what field they are. Those are for the abelian field z, for the non-abelian field z, for the abelian field I, for the non-abelian field I. This is for the abelian field 0 and for the non-abelian field 0. So this loses its source, and this as the only field, the only equation of motion with the source seems to be this one. But it's not actually true, because the Chern-Simons on the background solution can act as a source, as it did for the electric field, for the unperturbed baryon, right? So let us analyze more in detail a subset of these equations. And we write for sure the one that has the source, because everything must start from there. It's there that is present, the theta. And now it looks like this. And then, since, let us take a look here. And, sorry, let us take a look here. And this object will vanish, and okay, let us argue this later, but trying to see if I can speed up the thing, but okay, no need. Let us write all the sets. Then we write the one for the I component, the abelian part, and this is of the non-abelian part. No, this should be the abelian. Okay, of the abelian part plus the z kz delta f iz. And why I think this is the second most important? Because it contains f IZ, and this is the one that receives the source term. So somehow it can transmit to the other one. And then the Z field abelian also appears in the one for the zero field, because it appears here. And here we have Fij, Fkz. And we have already assumed one thing that is true, that the I abelian field, the I non-abelian field, sorry, this one, has no source term, and this other field here also will have no way of obtaining a source term. So we can set, no, sorry, this one will obtain a source term. So we can set the delta AM, sorry, to zero. I have to combine all the indices. Okay, so here I already went to check only the one in the abelian field. Okay. Okay, and then we have minus K H of Z delta then F0 nu plus delta Z K of Z F0Z equal to its possible source term, which will be Ej kappa F Ej delta F Kz. Okay, and I already used the fact that if the perturbation is on this side, then the abelian field on the background is zero. So this is the only term that can appear. Okay, now let us move our attention only on the abelian equation. Okay, so this set here. Okay, we are surrounding the source term, essentially going closer and closer to where the thing begins. And we have this equation for the Z field once we expand the field strength. So the J, the Z, Aj minus the J, delta Az equals to Cm theta 1 plus cosine of alpha. And then we have Hz, and then we have the nu F mu num. And one thing is that we don't include time dependence, so I can also use J and J here. It's the same, plus the Z, Kz delta F Z equal 0. So as I told to Claudio before, the time dependence is subleading in 1/n. So we can take first the static limit. Okay, now we have these two equations. They're coupled for essentially the coupled fields. I mean, they seem coupled. Then it's abelian. Then so they are not really coupled. Are these ones, and these as the source. So we know that only him will receive the perturbation, because these are abelian fields and they do not have a coupling between each other, so they will be independent. And what happens is that you can just assume with an ansatz. I mean, you can also see by equations of motion, but you can just start by guessing this. And then what you obtain is this kind of equation. Okay. So you have the equation for the perturbation. And then you see that the dependence is factorized. The dependence on Z is only here, but you see immediately that when you put this in here, then the dependence on Z, 1 over kz, cancel out this kz, and the subsequent derivative kills this whole term. And then you remain with this equal to 0, which is solved indeed by 0. Okay, by this first ansatz that we used. So it's perfect, and it works. And a solution of this equation will be simply given by AZ taking this form, Cm theta over K. Then we have U of R over Kz with U of R obeying on its own this equation. Okay, so this is the delta on front. So this is our first perturbation. And then what happens is that this enters here and can act as a source for the A0 field, the non-abelian one. So we have to assume an ansatz for A0, A, and there is only one possibility. The possibility is that the structure, the vectorial structure with the x's and taus, is something like a constant in front, of course, that we will fix later, and then a function that we call w of both r and z, and then x dot product with tau, and then a to the minus 1. And you see, there is no other option because this is a scalar, because it's the 0 component, and so it must have a scalar structure, but it must include tau, and because it has an index, okay, this is tau, this is without the a, it's just the index, the group index is included in the presence of the tau matrix. So it has this structure, and it turns out that the constant in front, we can choose it to be particularly useful one, is 27 pi Cm theta over lambda k, and then times a w of r and z x dot tau a to the minus 1. Okay, perfecto. And now we plug these ansatz into our equation of motion, and we obtain an equation for this function w. And again, this is a bit tedious, but we've already done it. And it is this, where now I tell you what are these objects. So this is our final monster to kill, because once we solve this, we can put the A0 and AZ fields into a definition of the holographic electromagnetic current that I will give later, and this can be solved numerically. No ansatzes to solve us, to save us numerically. And this is because this function W are functions of both R and Z. And it's not easy to solve with the partial derivatives. And the prime is a derivative with respect to R, and dots are with respect to Z. But I didn't use dots here, I think. No, okay, usually I could have used, okay, this is a dot, sorry. Okay, now we plug this thing into the electric dipole moment formula. Plug everything in ADM. So the electric dipole moment is given in general by the expectation value on a baryon state. So this is of a baryon, of a certain baryon. It's a vector. And you integrate the electromagnetic current with xi, and you see what comes out. And it is forced to come out a number that depends on the baryon and the expectation value of the spin operator. This is because this is a vector and the only vector intrinsic is the spin. Okay, I give the holographic electromagnetic current. So it is given by J mu vectorial tau 3 plus 1 over NC, the abelian vectorial current. And this expression in general, a current J mu vectorial, is given by the sum of the right and left current. And its formula in terms of the supergravity fields is Kz F mu Z evaluated plus infinity and minus infinity. Okay, so this is a map between the two objects. And we can immediately see that for us, the abelian term vanishes because we have the 0 delta AZ and the Z delta A0, abelian and abelian. But this will be 0 because it's a time derivative, and anyway it is 0. Yes, anyway, this vanishes, and this is non-existent, this perturbation. So the abelian part vanishes for us. It also vanishes because of this dependence, which is our AZ goes like 1 over K of Z. So vanishes, but we have this one, okay, which is different from 0. So it's very important that we found the non-abelian perturbation. It's the only one that enters the formula in the end. And so we plug everything, and okay, 1 minute late, but we are finishing now. Okay. And when you perform the angular integral, it gives you some solid angle. And then you have this formula derived from the current. This W function, we already know what it is, and we have its numeric solution somewhere in our computer. And then you have the part that depends on the baryon state, which will be, so I say N because it's for some nucleon, and then will be the neutron, but for now let's keep it general. And then S, which is a spin state. Then you have the trace of this operator, A, tau I, A minus 1, tau 3, and S. And then you have a factor that is mc theta, as always. And then we arrive to our final formula once we do everything. That is, for a neutron, what we end up with is minus 4/9 pi k mc theta. I forgot one thing. This operator here gives, you need to do the quantization of the baryon to see it in the model, but it can be done, but it's long and it was very tedious. So it was computed by Adkins Nappy in a lot of time ago. And so it gives minus 2/3, and you have the expectation value of the spin and of the third component of the isospin. And for the neutron, this gives, of course, minus 1/2. Okay. And so in the end, we have minus 4/9 pi k mc theta integral of this quantity plus infinity minus infinity. And here you have the spin operator. And if you compare with the definition of the electric dipole moment, you see that this number here is exactly our Tm. And then you insert your parameters, mkk, lambda, c, and nc, and you obtain a prediction, which is 0.78 times 10 to the minus 16 theta electron charge times centimeters, which is consistent with previous estimates. If you compare with the experiments, it still establishes the strong CP problem. But the fact is that with the, I mean, I won't say it's simple, but with a perturbative approach at these equations of motion, you obtain the result that is very difficult, almost impossible in real QCD. You have to use effective field theories, and even there is quite tricky. And it's difficult also in lattice QCD, I think, because there is the sign problem. And maybe Claudio knows a lot more about this. But there are some predictions also in lattice QCD. But for what I've read, it's quite tricky. So I think we can conclude. I am a bit late, but at least I arrived at the end completely. So.
Okay. Thank you, Lorenzo, for this very nice discussion about holographic QCD and also about the neutron electric dipole moment. So first of all, are there any questions from the audience? So there are no questions, so I stop the